We're going to talk about software security, and which is mainly going to be focused towards hacking Linux binaries. This is one of the important areas, and as a country, also we need to have this kind of expertise built in. And Especially, I was told that many of you are from the background of computer science and EC, and also have interest in cybersecurity. So I thought this would be a very good area to talk about, and it relates to whatever we have been learning throughout our courses in engineering, actually. So just an extension to that, more from the perspective of the security. And If you talk in terms of the word which is very commonly used in the security, it's called as pawning. So pawning essentially means like you're trying to own a particular process, service, or a device, and typically relates to vulnerability research and exploit development. So, though most of this, which I'm going to talk about, is Linux binaries, it also partially applies to Windows binary, at least at the conceptual level. But there will be slightly small changes when we do these exercises on a Windows machine. Uh, so the whole idea is like we're going to talk about vulnerabilities. Though there is a part of reverse engineering, I'm just going to skip that because that's like maybe within this time frame it may not be suitable. But I will talk about other three aspects, which are like exploit development, defense mechanisms, and fuzzings. So most of the lecture is going to be focused on Linux binary, and that too on the x86 processors, as Linux is very versatile and also can be made to run onto various other architectures like MIPS, ARM, and things like that. But today our focus is going to be on x86. Secondly, I'll also talk about certain tools. There will be a lot of demonstrations, and we'll try to map a lot of concepts to these demonstrations. So we will make sure that all what we talk about in terms of concepts is also demonstrated on a Linux machine running on x86 platform. So since this is like a very niche area, we require skills from multiple domains. And Also it's little system level components which we need to deal with. We need to have knowledge about processor architecture, how a processor works, what are the registers inside a processor, that kind of knowledge. Secondly, we also have to know how an operating system works internally. So how a process is loaded in the memory, how it executes, that kind of functionality. We also need to understand about tool chains. Tool chains are nothing but a set of tools which allow us to convert our source code into final executables or binaries. And these includes like compilers, the linkers, and sometimes when you want to also debug the things, we require debuggers for that purpose. Also, since we're going to deal with software, we should also understand what are the binary formats. Typically, like ELF and PE are the most popular ones, and we'll discuss more about it. We also need to know a little bit of reverse engineering so that we can analyze the binaries, file vulnerabilities, get a better insight of what's going inside and things like that. And saying all this, we don't have to have only theoretical knowledge about all of these things, but we need to have very good knowledge about hands-on in using the tools. Apart from that, we require a lot of patience because the results may not be that easily evident. But once you have the results, it's like very promising, and it's a great achievement in your career, actually. So let's talk about the terminology. So the first thing which we're going to talk about is the word binary. A lot of people use this word binary, especially when you talk about the binaries. There are other names to it. People also call them as programs, or they call it as applications. Sometimes when it comes to networks and things like that, like suppose an FTP binary, so it is also called as a service. So don't get confused if someone says that, okay, do you know how to analyze a program? He's essentially talking about binary analysis. Also, if someone says that, can you analyze this particular FTP service for me. So the FTP service would be developed using some binary as a server running onto the machine, but still talking about the binaries. When you talk about binaries, typically it's executable, and this executable will be different for every OS which you're running or the runtime environment you have. So, like just to give you an example of it, when you talk about Windows, it's going to be a exe format. When it is Linux, it's a ELF format, which is also called as executable and linkable format. While on the Mac machines, it's called as a Mac OS. So there are various other formats also, but these are like the ones which are very prominently used. So let me just show you a small demo of this. Uh, so here you see that I have various files actually. Have a look at this exe file. So though I am on a Linux machine, I have compiled this program to run on a Windows Linux machine. And if I do use this command called as file and give the input as main.exe, you'll see that it tells me the details that this is a PE format. So what essentially it means is portable executable. So PE stands for portable executable, and that's the format which the Windows machines use actually. And also tells that it is an executable which can run on a Intel x86 based processor, and it's going to be having requires a runtime environment of Microsoft Windows actually. Same way, I have compiled this C program also into the Linux ELF format. And if I look at it here, you'll see that when I take this binary and it to this utility called as file, it tells that it is a ELF format, which is ELF executable and linkable format. It runs on 64-bit, while this was on 32-bit, and is also on a x86 but 64-bit platform. Now there are tools, so this is like very important for anyone to understand that what is the file format they are dealing with, so that the analysis becomes easy. So essentially, what I wanted to tell you here is uh, sometimes the extensions can be fooling. So even if this is a exe extension, it does not mean that it might be a binary. So just to give you an example of it, I can take this main executable and I can name it as exe. So when I say it is a main new.exe, it doesn't mean that it is only going to run on a Windows platform. So we'll have to really find out what exactly it is. And we can use this file command to know it. So you see that though the extension is exe, but it is an ELF format which works on Linux platform. So
Sir, if
what I
you
sent,
prefer, you can share your screen also, sir.
thanks for letting me know that. Sorry, so I think maybe I'll have to repeat which I talked about. So I'll just quickly do that. So this is what is the focus of the talk which I was telling about. And apart from that, I told about the skills which are required for us to understand this domain. And I was just talking about this terminology in terms of binaries. What do you mean by binaries? So as I told, like binaries are also programs, applications, or services, and they are in these formats like exe, ELF, and Maco. And that is what is the demo which I was showing you. You are able to see my screen also, the terminal.
Yes, sir.
Yeah. So here, if you see, like I have so I can compile this C file. So here you have the simple C file. I'm just using the compiler to generate the output of it, and you see that I get the output. So I have output as main. Similar way, I have also generated an executable format, and I can use this utility called as file to tell me what exactly each of these files is. So here you see that it tells that the main.exe file is a P32 format, which runs on a Windows machine. While if you see the main, it is a ELF 64-bit platform, which runs on a Linux machine actually. So essentially, what I wanted to tell is like understanding the binary formats is very important for us. because that helps us to use the right tools for doing the analysis. So let's understand these concepts, like what is a program versus a process. To look at this program which we compiled, we have a main executable, which is elf executable on our hard disk. So this is on my hard disk and it is inside this particular folder, right? So this is a program. So we call this as a program because it is a dormant executable file. It is passive. The OS does not know about it as of now. And these programs are sometimes also called as executable code or executable file, or even a binary or a executable program. And as I told you, it resides on a hard disk. Now, how do I convert this into a process and make it active? So, as we would have studied in OS, like a program under execution is what is nothing but a process. So, this program, if you run it, it becomes an executable and a process, running process. How do I run it in Linux? I do it this way actually. So, when I run the main program, so what happened is this program was taken from the hard disk and it was loaded in the main memory. So just to make you understand what happened is this. So we had a program on the hard disk. This is the first step over here. We compiled the program and then we ran the program using dot front slash and that. So when we run this program on the shell, we are indirectly telling the operating system that take this program from the hard disk, which is dormant, not active now, and make it active. So that is this third step where the program gets loaded into the RAM. So the moment the program gets loaded into the RAM, it starts executing and it is called as a process. But this looks very easy, but most of it is like abstract to us by the OS. But let's go and look slightly more deeper into what internally happened, right? So every program which you write in C requires these five sections to be available in the RAM. So there is a concept called as address space. So when you say address space, it is nothing but a chunk of memory which is there in the RAM, which the OS allocates to us. So when we run the program using dot front slash main in this case, or in this case greet, it is copied into the RAM, and there are these five segments that are created, and appropriately from the program information is extracted and put into this segment. So let's understand what are these segments actually. So the first segment is called as the text and code segment, which holds, as the name says, the instructions inside a program. So as we all know that every program has to be written with some statements, and finally it is converted into assembly code, or also the machine code in raw byte format, and that information is stored inside this code segment, or also the text segment, some people call it. We also have similarly data segment for initialized data and uninitialized data. Apart from that, there are two important segments called as the stack segment and the heap segment. So the stack segment starts from the top of the process address space, as you see over here, and it grows downwards. Same way the heap grows upwards, right? So, and this whole thing is called as the address space. So let's take a sample C program to understand that how it is mapped into each of these. So here's a very small program wherein it has a global variable var1 and var2. But you see that apart from that, it also has functions like a func and a main function. So let's see where what goes into the text segment. So if you see here, whatever is the statement or the logic that we write inside the a func is going to be the set of statements in the C program, which will be converted into assembly and then put into the text section. Those are called as program opcodes, and that is what the text section is going to hold. Now let's have a look at these two variables which are global. So var1 and var2 both are global variables, but there is a difference between both of them. One of it is initialized. The var2 is initialized to 10 versus var1 is not initialized. So whichever is the initialized global data, it will always go into the dot data section, while whichever is a uninitialized global data will go into a special segment called as a .bss segment. So this is how these global initialized and uninitialized variables are mapped to the memory. Further, if you go, you see there is a special variable here, which is a constant of type, right? So constants would not change their value. So they go into a special segment typically called as a .ro data. So this would be slightly different in different case compilers and things platforms. But essentially what it means is this variable is not going to change its value over its execution. Then the next one is nothing but the variable lock. If you see over here, we start executing the main function. Inside the main function, you see that there is a local variable called as double lock. This double lock is a local variable, and there are two places it can go into. It can either go onto the stack or it can go into the registers of the processor. Now, this is very important for us to understand because most of our lecture is going to be around this. And here we are talking about x86 processor. So on a x86 processor, typically the local variables will go onto the stack. As you see over here, this place it will be allocated. And then you also have this another statement called as malloc. And you would have also studied that malloc typically is a dynamic memory allocation, and it is allocated on the heap. So essentially, now if you look at the entire C program, you take any complex C program, it's going to have a global initialized and uninitialized variable. It's going to have a set of statements. It's going to have local variables, and it's going to have dynamically mapped memory, allocated memories. So what happens is all of these will find a place into one out of these segments, and that is the reason we should understand these segments to see that how program executes, and so that we can do further security analysis on the program actually. So if this is understood, let me just quickly ramp up what we have been talking about. We have global initialized and uninitialized data that will go into dot data and DSS correspondingly. And there are statements which will go into the dot text segments, which are nothing but the machine code or the assembly equivalent code of the program, your algorithm or logic. And anything that is local to the function will go on the stack on a x86 processor, while anything that is dynamically allocated using malloc, calloc, and other friendly functions, they will go on to the heap. So that's how the whole program is loaded into the main memory and allocated. So if we have understood this, let's go and yeah. So let's go and talk about the security aspect of it. So the vulnerability and the exploit development. See, if you talk about any software, we talk about two aspects of it. One is the correctness, and the second is the security of the. So correctness means like what the particular software or the system is supposed to, and it is a desired behavior. So if it's an FTP server, it has to do FTP functionality, right? So if it is a financial software, it has to do only financial related. But what happens is because not every software is going to be perfect. It's going to have some bugs inside it. It can arise to security issues. So typically, when you talk from the perspective of a security engineer, he would say that okay, this software is not supposed to do certain aspects actually. So we actually talk about what it is not supposed to do, right? And if it is doing that, then it is something dangerous because adversary or a malicious actor can typically then go get a control over your program or the system because of this. And today we are precisely going to demonstrate the same behavior. So given a particular software, how the adversary or a malicious actor can get a control over your program and execute anything what he desires on the system actually. So before that, let us also understand this terminology called as vulnerability. So when you talk about vulnerability, it's typically a bug inside the binary. So now we know what is a binary. It's a program or application which is there. and typically the vulnerability is exploited by a attacker. So what do you mean by exploit is nothing but specially crafted data which is sent to binary as a input, and then the binary starts misbehaving, right? So that is typically called as the exploit, and this whole process is called as exploitation. How a lot of people disclose vulnerabilities, and if you as a security engineer you find a vulnerability which is not publicly known either to the vendor or to any of the public mechanisms, then you typically call it as a 0 day. So when you say 0 day, it means that you have 0 days to fix that particular vulnerability. And essentially, that is what is people even get highly paid to find a 0 day in the system actually. So let's understand how the attackers breach the system. So if you look at you have a secure SDLC, right? Typically while developing any software. Man. So attackers would typically now exploit the vulnerability. So what is a vulnerability? We thought it's a bug. So that bug is exploited by the attacker. So the this software bug is actually also generally called as a defect. So you don't use the word bug. Defect is the generic word which is used, and defects can occur in a system in two places. One is during the design time or during the implementation time. If a design is found something wrong at the, then it is also called as a flaw. So when I say there is a flaw in the system, it means the design itself is wrong and some security adversary can actually get a control over the system, and so which is much more dangerous because it's very difficult to fix a flaw. Same way when you talk about implementing something, so we have developed a software using C, C++, or Java. If you find any defect in that, we typically call it as a bug actually. So today we are going to talk mostly about the implementation related defects, which are nothing but the bugs. So just to correlate everything what we have been talking about, if we are able to get the right bugs, okay, so which are nothing but the vulnerabilities that are inside a particular binary, then we can write exploits which can hijack the execution of the program. And this is what we will demonstrate at the end of this program. What is that attacker would get if he's able to do this particular functionality? He can gain privileged information. He can download and install additional malware onto your system. He can steal data onto your system, or he can just create a havoc on your machine. So he has complete control over your system. So the type of vulnerabilities we are going to talk about is related to buffers. Every one of us knows that what is a buffer. Typically, a buffer is nothing but a contiguous memory location which is allocated. And there would be many times when we write programs in C, C++ that we require buffers. Like for example, a packet, incoming packet is there. I want to process it. First, I'll put it in the buffer. Or if there is a file which I have to read, so I will read it and then I'll put it into a buffer. So it is just a continuous memory location in the RAM, right? And when you talk about C programming languages, they typically arrays, and sometimes they are also as strings, which is nothing but typically null terminated. What is the problem associated with it? So see that there is no bound checking of these buffers in case of C, C++. Because if you try to read any data beyond the buffer, the OS allows you, or even the C programming language actually allows you to do that, right? While if you see, if I do the same exercise in Java, it will throw an exception telling that okay, there is an array out of bounds actually, which clearly says that there was a fixed size of buffer you're trying to access beyond that particular buffer. But that is not true in case of C and C and C++, right? So let us, I think, let's see a small program. do this or understand this. So here I have here I have a small program which is written. So let me just show you the program first. So you see that it's a very simple C program, and I have a buffer here. So as we said, buffer is a continuous memory location, and this buffer is now here of size 5. It holds 5 bytes because each character. And what we are trying to do here is copy some data into this buffer, which is of size 4 and maybe 5, including the slash n part of it, right? Now, if you try to see, I have just put a simple for statement, and this for statement is going up till 0, from 0 to 9. So it means it is going beyond this 5 bytes of data which is allocated here, and we are just printing the its index and also its value in the character format in hexadecimal format, just for our understanding. Same way, so it means like essentially what has happened here is the buffer what we have allocated is of 5 byte size. So this is the buffer, and so this is the buffer of 5 bytes. So, and we are going on reading beyond this 5 bytes here actually, right? So what is the for loop? While here we are doing the same thing, but we are reading 5 bytes beyond the buffer size, right? So essentially, what we are trying to do in the second case is like we are reading this side of the buffer, the left hand side of the buffer, right? So let's run this program and it comes in. So we have compiled the program and we are running it now. And if you run the program, you'll see that the 0th location, the letter H is there because HACK, as we mentioned. So HACK, the string ends over here. But you see that we are able to read the 5th location, 6th location, 7th, 8th, 9th beyond the particular buffer. And that is true on the reverse side also. So data minus 0, minus 1, minus 2 memory locations, we are still able to read it. So it means both side of this buffer, we are able to read the data. Now this is a major problem, and that is what he's talking about. So it is possible to index value outside of an array in case of C and C++. So this is what exactly we demonstrated using this program. So so the actual terminology in security is called as buffer overflow. So what exactly it means is you are able to go beyond the particular buffer indices or allocated buffer indices and cause the program to misbehave, right? And typically what happens in many cases is when you try to do this, your program will typically go and simply crash because you're trying to access beyond a certain. So if we try to go maybe 100 bytes or 200 bytes, the OS then puts a restriction and then says that okay, now you're done and you have to terminate yourself, and that's how the program crashes. In fact, from the perspective of security, if you find a crash, it is a good thing because it means there is something which the developer has not handled properly, which as a security engineer you can actually exploit. So that's a could lead to a vulnerability. So that bug can typically lead to a vulnerability. So what can an attacker do? If I have something like that, I can crash the program, or if I have a very good control, I can even corrupt the valuable information inside the process itself, which is also possible to do. I can steal private information, and this is exactly what happened during the Heartbleed, one of the major bugs inside the OpenSSL, wherein they were allowing us to read data from the client side beyond a particular buffer size actually. So what happened is regularly it was sending heartbeat informations, and in that heartbeat information typically used to send what how much data you want to read. So if I say 5, it would give 5, but if I say 10, 20, it still used to go beyond the buffer size and read that additional information for it. And then most dangerous out of that is nothing but, as an attacker, I can run any piece of code onto my compromised software or the buggy software. So the good thing is we'll try to demonstrate all these four types of things possible on a binary, actually. So you might be wondering why he's talking about C, C++. If you see, today almost everything still survives only on C, C++, though you have these languages like Java, Python, Ruby, or JavaScript on the higher side. But whenever it comes to critical system, which includes even your operating system kernels, even today they are written in C and C++. You talk about even the most high performance servers like your Apache Nginx or HTTP and IIS web servers, they are also written in C, C++. Same is true with the databases and the popular Redis and Memcached utilities, right? And not to forget, but even today, a lot of people write code only in C, C++ on embedded systems. So if we understand this C, C++ bugs, we can actually get a control over all these critical components, and the attacker can actually create a havoc because of this. So that's why it's very important for us to understand these concepts. So if you actually go, there is this website called as Common Vulnerability Enumeration. It is CWE. It is called as. Even today, the buffer overflow exploit is on ranked second in the whole top 25 list. It means most of the software is still vulnerable to buffer overflows, and that is what is exploited. And when we say a buffer overflow, it could be a overread or a overwrite also. So sometimes you can read the data. The example which we showed you just now was like reading the buffer data beyond it and ahead of it also. So both aspects of it. But sometimes you can also write data into it. So in future, whatever we are going to show the demonstration is going to be writing the contents beyond the buffer size, right? And like typically it can be for anything. It could be addresses or data which can preside this particular buffer, and we'll see that aspect of it also. So let's start with. So I already showed you a demonstration of buffer overread. So now let's go deeper into the whole idea and see that how it works. So if you see, you start typically with an algorithm. Okay, that is what is your aim actually, right, man? And once you have an algorithm in your mind, you start coding for it. That's where you start writing the program, and this program is then compiled and then converted into instruction, right? So when you convert this whole content into instructions, and that is what actually you would so that is what you typically store, right, the instructions into the memory, and that goes into the part which is nothing but the code. So all the code segment is what is going to hold your instructions for, or the algorithmic logic of your program, right, man? But the algorithm cannot be on its own, and it requires data, and that's why you have this data segments, right? So data typically would come from an external agent most of the times. Then it is stored in the data memory. Then these instructions apply it their algorithm on the data, and it generates the output that is also going to an external agency. Just to give you an example of it, I receive an HTTP request that is coming through an external packet, right? So it comes into the data memory. My code in the HTTP server does a logic onto it, and then responds back as an output to that particular. So this is a very common flow, and there is a very clean demarcation between what is code versus what is data, right? So here's a small example of a program, and this program, what it does is takes a username as input, and assuming that the username is going to be 12 characters in size, it goes and stores that username inside the data memory. And the code from here in the code memory goes and accesses that data and verifies that the username is correct or not, right? So this is how actually it would work. Okay. Now, if you actually go deeper into this, you'll see that I have sent the username here as C-DAC, which is a string, which is good because it is less than 12 characters of size, right? And that's why nothing will go wrong and everything will work fine actually. But instead, assume that I send a chunk of bytes here. So if you see over here, I'm sending you a chunk of bytes as input to the program. So it comes as an input and it is stored inside the memory. But when it is stored inside the memory, though it is a chunk of data, I have carefully, as a malicious user, crafted it such a way that they are nothing but set of instructions instead of data. So they do look like data, but if you look at it carefully, it is nothing but a set of instructions. So if, as an adversary, I am able to control the flow of your code over here and jump to this particular data, which is actually a set of instructions, then it means I am able to execute this set of instructions inside the data memory. And then I am able to control the entire execution or what functionality I want to execute on your system, because this input is crafted by me as a adversary actually. And that is what essentially at a very top level happen. So the set of instructions is what is going to be sent to you as a data, and that is what is going to be stored inside the data memory. And somehow the user will get a control, or the adversary will get a control over your execution flow and jump to this data. When he jumps to this data, it will start executing this set of instructions onto the data memory, and he'll get a control over this flow. So this looks little complex, but I can show you a demonstration that how easy it is, though it is a little involved at starting, but once you understand the concept, it becomes very easy. So let me just once again come back to this memory segments, and let us understand some more details about it. So the most important over here is like definitely the global uninitialized and initialized segment. You see that A is uninitialized, so it goes into the BSS segment here. B is 20, which is a global initialized, so it will go into the data segment. You see here. While you have a main function now. Now there are two important things on the main function, right? So if you see, the main function has arguments, so argc and argv. In fact, this argc and argv are also stored on the stack. If you see over here, they are on the stack. So it means the parameters to a function is stored on the stack. So as you see over here, argv and argc. The second thing to understand is they are in the reverse order. So if you see argv is first stored, then argc is stored. So argv is first stored, then argc is stored here, right? Second is nothing but you also have the local variables. You see here p and buffer. So they are also allocated on the stack, right? So this buffer of 120 bytes is onto the stack, right? So essentially, if you have understood this whole concept, what we'll have to remember sufficiently enough to understand the whole concept is local variables are allocated on the stack. So let's go ahead and understand some more details in terms of the processor registers. So as a security engineer, you may not have to have expertise in the entire assembly functionality, but it's always over the time you will gain it. But at least these three registers are very important. One is the ESP, which is called as a stack pointer. Second is the base pointer, EBP. And the third is nothing but the EIP, which is nothing but the instruction pointer register. So you can go to this website and you can actually understand more about it. But let's just to summarize, these three are the registers we should worry about. So the EIP points to the next instruction that has to be executed in the processor. So you remember that the .text section was holding a set of instructions. So this EIP register, which is a 32-bit register on a 32-bit x86 architecture, is going to point to that particular text section, especially to the instruction which has to be executed next. ESP is nothing but the stack pointer, and as you all know that the stack is nothing but going to have a pointer which points to the top of the stack. So this ESP register in hardware is typically that register. So all these registers are in hardware, and then you also have this register called as a base pointer. So base pointer register typically helps you to point to the frame pointer. So whenever you call a function, there is something called as a stack frame that is created on the stack. So how do you access these local variables? They will be all accessed using the base pointer, and that is what is the purpose of that register. So we're going to see an example of it so that you understand it much better. So you see that here's a main function, and from the main function we are calling the function foo, and the foo is taking arguments as 1, 2, and 3. So it goes to the foo function here, and it copies those a, b, c into 1, 2, 3 respectively, and it also has local variables. You see that the foo function has local variables x, y, and z, and it just calculates the addition of it and then returns the z. So let us see how it looks onto the stack. So this is how it looks onto the stack. So right now your stack pointer is pointing to this location, and when you say a, b, and c is passed, so these variables first are going to be put onto the stack. So if you see here 1, 2, and 3, which is nothing but equivalent to a, b, and c, so they're going to be pushed onto the stack. So initially the stack was totally empty over here. You see it is pointing to the empty location, but the moment you call this function foo, the first thing it will do is put the c variable onto the stack, then the b, and then the a. It is always going to be in the reverse order actually, right? And once you put that variables onto the stack, then after foo finishes its execution, it has to come back to the main function. So how does it come back to the main function? It holds that information in this return address. So on the stack itself, it holds the return address for that function. So that would be immediately after you put the parameters. After that, it also requires a frame pointer. So the EBP register is used to access the ABC arguments as well as XYZ variables, local variables. So these arguments and these variables, local variable, how it will be accessed is using the EBP register. So what happens is the old value of the EBP is saved on the stack so that when it returns back, it is retrieved. So this 4 bytes are meant for that particular. And then you see that you have the variables x, y, and z. X, y, and z, which is stored onto the stack actually. So this is how this whole thing is called as a stack frame. So whenever you call a function, a stack frame is created. Whenever you return from a function, a stack frame is deleted. So essentially what we have to remember here is when we call a function, the arguments to that function are put in the reverse order onto the stack. Then it holds the return address onto the stack, which is nothing but where it has to return back. Then it stores the base pointer of the main function followed by the arguments, local variables. So here x, y, z is local variables too. This whole thing is stack frame actually. So I think this is very important for us to understand because all our exercises next would be based on this. So let me just jot it down onto this Excel sheet so that we understand. So as what we understand, the first thing what is put onto the stack is nothing but the params or the arguments of the function, then the return address, then the old EVP value, and then followed by that is the local variables. So this is like these are the things which we are going to actually store onto the stack. This is the sequence of the information stored on the stack. So let's go ahead and so what do you mean by buffer overflow now? So if you see in the program, we had a buffer which is a local buffer, right? So here you see that there is a local buffer. So can you guess where this local buffer would be stored? So if you guessed that it is on the stack, and as per our discussion over here, it was very clear that local variables are stored on the stack, right? So like XYZ is going to be stored on the stack, and since the buffer is declared here, it is also going to be on the stack. So what would happen is now we know that the sequence is like this: the return address, the frame pointer, which is the EBP register, and the buffer. So when you put the data hello in it, since it is less than the buffer size, it will hold the data correctly. But what would happen if I go on sending a data which is more than that buffer size? It goes and overflows into the frame pointer and the return address. And that is where the whole problem comes in. So essentially what has happened is we have caused a buffer overflow. So let me just show you a small example of it so that it's easy for us to understand. So here's a very simple program. So what does this program do is nothing but it takes the argument from the user, and it just so here if you see it just defined a local buffer. So can you guess where this username would be allocated? So since this is main is also a function, since main is also a function, and this is a local variable to the main, the username buffer will be allocated on the stack. So you see that local variables are on the stack. So this username buffer of size 16 is going to be on the stack. Right? So you see that it is of size 16, right? So this is of 16 bytes in size. And what is how do you get the data inside this? Using a scanf function. So scanf is nothing but going to take input from the user. So as a user, I'm going to pass the details, and it will just print and put it into this buffer. So let's go and run this program and see like what happens. Here it is. Mm. So we've compiled the program, and I'm running this program. So it is asking me for username. So I just enter a very simple username, which is Mahesh, and it exits properly because the size of it is MAHESH, which is only some 6 bytes of size. So you see that I have only occupied some 6 bytes, but I had actually allocated 16 bytes. So it is fine. There is no issues. But let's go and give slightly more to the same program. Now let us give 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 bytes as input, and it still works fine. Let us give 17 bytes. It still works. Let us give slightly more, 18 bytes, 19 bytes. And slowly now you would see that after a certain time, the program crashes. It means that after a certain set of bytes, what has happened is the program crashed. And this is what is the first thing which we discussed about actually. So if you remember the slides which I was talking about here, what can an attacker do? So an attacker can actually, yeah, that attacker can actually crash the program. And this is precisely what is shown in this example, that by giving a buffer overflow which is more than the allocated size, I can actually crash the program, which is also popularly called as denial of service attack in the world of security. So this is the first thing we have demonstrated. So as an attacker, I can crash the program. The next thing we'll see is whether we are able to corrupt any valuable information on the program actually, right? So for that, let us also understand another program. So this is what we are going to do now. We are going to change the variable inside a program. So for that, I've written a small program here. So let's understand this program. In this particular C program, if you see, we have the main function and we have a variable called as flag. So now let us draw the stack for that. So here on the local variable, we also have a flag, and followed by the flag, we also have a username. So username here, and this username is of 16 bytes in size. correct? So what has happened is on the stack, we have the flag as well as username. And obviously, since this main is also a function, it's going to have these two things here. It's going to have an old PPP end. Now the whole program says the concept. So look at this variable flag. The variable flag is never changed anywhere in this program. So do you see that any assignment having to the variable flag? No. Here, what we are checking is variable flag is equal to 0. Is it equal to 0? Yes, it is equal to 0. So it means that when we execute this program, it is always going to print this function, right? So it's always going to say flag is 0. Why? Because if you see the lines before this, there is nowhere we have accessed the flag variable. Did we access? Only once we have initialized it globally, and after the global initialization, we are just checking whether it is 0 or not. And if you see, it is more like this else statement will never be executed, right? But now you see that there is a small piece of code over here, which is nothing but taking the argument, the first argument that is passed to the program, and copying it into the user buffer. Now, just have a look at this. What is happening is we are taking an external input and passing it to the buffer username. Now, if this is less than 16 bytes, there is no problem. But what would happen that beyond the 16 bytes, if you put, it will go and override the flag register, because these two are very near to each other in the memory, stack memory. So beyond the 16 byte, the flag variable will be changed. And when the flag, after you copy that arguments from the user input into the user name buffer here, it will go and change the flag variable, and it will also have a control to execute this piece of code, which was not possible earlier actually. So this is how the attacker can get a control over your execution flow by sending a set of input bytes. So you see that this is what is the powerful nature of the buffer overflows actually. So let's go and execute this piece of code. So that is this is the same program which we talked about. So the flag is never changed. Let's run that program first. So when we run, it asks for the arguments. So let's pass some argument. So I'm passing which is a small argument, right? So it doesn't cause any problem. So it's always going to be 0. Additional a still going to be 0. But let me just pass 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is going to fill the buffer 16, right? So the buffer is now filled with 16 A's. And additional A over here will go and override the flag variable. So it means if I pass an additional A over here, which I did now, it's going to pass and put the data into the flag. And you see that now we are able to execute the else statement where the flag is non-zero. So here, if you look at the C program here, we never had the flag variable changed. But just by the input that is coming in, we were now able to execute this statement over here and get a control over the execution flow. And any guesses that why the flag value was printed as 97? So if you understand the way the information is stored, like this is, we have passed the character A, and the character A decimal equivalent of it is nothing but 97. So if you look at the ASCII chart, if you go and look at the decimal equivalent 97, okay, it is nothing but character A, and that is precisely what we have got. So when we pass character A and print it out as a decimal value, it is going to be 97, because if you see in the program, we are printing it as a decimal value, percentage D. This is what is the whole game about. Now you are able to control the variables also inside the program through an external input actually, and that is what is the powerful nature of your buffer overflow. So let's go back to our presentation. And if you, now if you look at it, we are able to do this, right? So we are able to change a particular variable by an buffer overflow. So next one is a little difficult to understand, but doesn't matter. We will try to show a demonstration which will make it very easy, right? I'm going to show you a piece of code. So let me just show you that piece of code first. So here's a piece of code, man. So in this particular piece of code, do you ever see any place where this secret function is called? So can you see that anywhere the secret function is called? No. So how the program flow will go? It will first come to main. It will check whether two arguments were passed. If the arguments are not passed, then it will just exit. If the two arguments are passed, then that argument is also passed to a function called as vulnerable function, which is here on line number 10. So this function takes that data which is passed by the user, and that data is copied using strcpy over here into a local buffer. Can you see there is another local buffer here? So means the argument which is passed by the user travels and then goes and sits inside the buffer here. And then it just says buffer copied, and the vulnerable function will return back to the main function, and then it will return. But nowhere we have called this function secret. Did we call it? No. If the secret function was called, it prints out some statement saying, cool, you cracked it. Now, our aim for this particular attack is nothing but you should pass the argument such a way that it overrides this buffer, but it does not override only the buffer, but also the return address of it. So if you remember here, when we talked about it, so you see that when in this case, okay, so let me just get rid of this. And so you see that you have the old BPP and the return address, right? And then above this, you have a buffer, right? And in this case, the buffer is of 64 size, right? So this is like 64 bytes in size. So what you have to do is you have to override this data in such a way that this return address should point to the secret function. That is what is the. So the secret function is something if you can override as a return address, when the vulnerable function returns, it will not return back to the main function, but instead from the line number 14, it would actually go to the line number 5, which is nothing but the secret function. So what you have to do is in the return address of the vulnerable function, put the address of secret function. Now, how is that possible? So let us just understand it first level. So in this program, is the secret being called? You see, it's never being called actually. So when you execute this program, secret is never called. So where is the buff allocated? So if you see buff here is allocated on the stack again. So it is going to be on the stack. And where is the return address of the function main stored? So it means like, where do you think the return address would be? It's going to be stored onto the stack itself, right? So if your answer is stack, then it is correct. And you see that it is never called, right? So let's understand. So you see that you have the buffer. So this is upside down. So you have the return address. Yeah. So you have the return address. That is this return address. Then the EBP value, and then above that you have the buffer. And this is the buffer you want to overflow and then write. So for that, first thing we have to understand is what is the address of the function secret. So to understand the or find the address of the secret function, so let us go to that. We have compiled this code. This is the same code which I have showed you. Right? So this is the secret function. So we want to know what is the address of this secret function. So we compiled this code. Okay, so this is the compiled version of the code. So let's go and use this utility called as readelf. So readelf is a utility which can read from the elf format, ELF format. And in this case, we want to read from the binary, which is buffer. Correct? So this buffer binary is what we want to read, and let's go and see what is the content of it, right? So these are all the symbol names, but what are we interested? We are interested in the functions only. So I'm just grabbing it with functions. So these are all the functions inside it. So you see that you have the main function, and the main function is at an address of this. Then you have a vulnerable function. So you see so you have the main function, vulnerable function, and the secret function, right? So main function, vulnerable function, and there is a secret function. So what is the address of the secret function? So if you see, this is the address at which the secret function is. So let's copy this address, and let's remember it somewhere. So this is the address of the function, right? So this is the place where we have to put the return address. So what we want to do is the secret function over here, we want to put the address 8048. So what happens is when the program returns back, instead of returning to the main function, it will return to the secret function. Let's go ahead and see how we can do that, right? So for that, I just use a very simple Python program. So let me just show you that Python program here. So first thing is we have to find out the offset at which this return address is. Okay. So you see that there is a return address. How do I know that what offset this return address is, right? So I'll tell you a small trick for that, and which is very easy trick. I use this tool called as GDB Jeff, actually, which is a debugger. So GDB is the most popular debugger in case of Linux. So I use an extension called as Jeff, which allows us to get some more details from the perspective of vulnerability analysis and exploit development. So I'm just passing it out there, and you see that it starts the program. Okay, so it starts, and you see that the program is ready now. So what I do is I put a breakpoint at the function name so that it goes and stops there, and I run the program. So I should run it with some argument. So to get an argument, I can generate a pattern. So I say that create a pattern of 100 bytes. So it generates a unique pattern of 100 bytes here. And this is what we want to pass it to our program. So this R means to run the program, and run the program with this argument. That is what I'm telling it actually. So this is 100 bytes, and definitely the program is going to crash because of this, right? So you see that when I run the program, it stopped at main, and then I continue the execution and it stopped. You see that it says that the buffer overflow program stopped, and it stopped at this address, which is nothing but the address in the EIP. And we discussed about EIP, which is nothing but the instruction pointer, right? And it's a segmentation fault, so it crashed the program. We want to find out that. So what essentially has happened is we took that big buffer, whatever was generated by the pattern creator, it created that buffer, and it wrote some data into the return address. And what was that data inside the return address? This is what is it, because that is what is pulled out of the stack. So now we want to know that this is at a what offset. So if I see, like, I can say that pattern search for this data in the pattern. So when I search for this data in the pattern, it says that it was found at an offset of 72 bytes, and it is for a Little Indian because x86 is Little Indian processor. So it means 72 bytes from here is what would be the return address. So if means 72 bytes after this, if I put this value, it will call the secret function and not go back to the main function actually. So let's see whether that is true or not. So for that, what I've done here is I've written a small program in Python actually, right? So if you look at this program, what it typically does is it takes a bunch of A characters, which is 72 in size. So if you remember, our offset was 72 in size. So we are creating a bunch of A followed by an address. Now this address should be the address of our function where the secret is lying. So where is the secret function lying? You see, this is where we found it, right? So what we'll do is we'll replace that address with this. That's it. And with this, we are able to create a payload which will contain 72A followed by a return address at this. And this is what we're going to pass it to our binary. How do we do that? So what we'll do here is we will run the binary and we will use this command Python to telling that execute this program Python, right? And this is what is going to be the input. And you see that after we ran this, there is an additional output here, which is nothing but cool, you cracked it. Now, when would this be executed? Only if so if you actually look at the C program now, secret function is never called, but now we are getting this output. It means indirectly the buffer is overwritten in such a way that we are able to override or we are able to take a control over the execution flow of the program actually. And this is precisely the output. So after that, like if you pass any other output, right? So if you see like buffer overflow, if I pass A, it still works fine. But if I pass any other string, it just causes a segmentation fault, right? But it does not call this function cool, you cracked it. It is only possible after we execute this Python script. You see that? And why it is possible? Because the Python script is creating that buffer for us. So the buffer is nothing but a set of 72 A's followed by the address. So you see that we are doing a +1 with the address. So essentially what has happened over here is this is like 72 A's. These are all 72 A's totally. And then followed by that is nothing but the address of the secret function. And that's how the attackers get a control over your programs when you call the buffer overflow. This is what we have done now. So you see that we have put more than those bytes, and then we are able to get a control. So this control, this finishes the demo, which talks about this part of it. We are able to get a buffer overflow function call. So you see that an attacker could do so many things. You could read the data, you could overflow and crash the program. He could go and change the variables which are in the vicinity of your buffer using like similar to the flag. He was able to call a undead function. That function was never called in your program, but the attacker could still call it by framing a set of input data that is going to your program, and he is able to get a control of your execution flow. Now, the last one is what we are going to discuss, which is nothing but the getting the code itself being sent. Actually, so as I was talking about, this is more sophisticated, and here what is happening is we are sending a code to the program, and that code will go into the data memory of the program. It will execute it in the data memory, and it will give us back the executed code actually. So we have got now the full control of that particular system because of this. So let's see how the code injection happens. That's called as code injection because you're injecting the code inside the process or the binary, right? So the program for this is here. So what we are doing is the same thing. So what we're going to take is the argument and pass it to the vulnerable function here. And that vulnerable function just copies the buffer into the 64 byte size of local buffer. So this buff is the argument, buffer is the local variable. So the same logic, everything is slow, but instead of the data, now we will execute the shell code. So let us understand the whole concept using a diagram so that it's easy for us. So what has happened is this is our 64 bytes of buffer here. So after the buffer, you know that there is a EBP pointer, the base pointer, then the return address, and then the parameters. So I've just switched the stack. So the higher memory is over here and the lower memory is here. Just for easiness, I have shifted the stack actually. And your buffer starts at suppose FFFF ABCD. So that's the starting point of your buffer. So let's go ahead and see what we can do. Now, the code which we want to execute, what we will do is we'll store it inside the buffer. So you see that a shell code is stored inside the buffer. And the remaining part of the buffer, if we just put the address, starting address of the buffer, so which is nothing but this FFFFABCD. So which will go and override the return address also. So you see that here on the left hand side, there is a return address. Now the return address will be put with an address of FFFFABCD. So the instruction pointer or the processor will go to this location and start executing the code. And what is there on this piece of code? It is nothing but our shell code. So essentially, it means we are able to now execute this set of instructions which we have sent as a part of the input to this buffer actually, and we can now execute our piece of code. So what is this word called as shell code? Now shell code is something which was invented long back. The first level of buffer overflows in the early days, they used to invoke a shell to prove that our code got executed or the attacker's code got executed. So for that, this typically a set of assembly instructions which are converted into byte codes, and the byte codes look like this. So for this particular shell code, which is using execv. So if you know Linux and even in some of the Windows machines, execv is a set of APIs which allow you to spawn a new process. And in this case, we are saying that spawn a new process with a program /bin/sh, which is nothing but a shell program, right? To achieve this functionality in Linux, you have to write these 10 sets of instruction. You see, these are the 10 instructions we need to write. And can you guess how many bytes of code it is? It's only 23 bytes of. That means 23 bytes of this code, if I'm able to inject inside a process and start executing it, I may be able to get a shell as an output of this. So this 23 bytes can be encoded this way, as you see over here in hexadecimal, and put inside the memory. So that is what is a shell code. So where do you typically get the shell code actually? So if you go and look at the, so if you go to this website here, it is shellstorm.org /shell code. You will get a set of shell codes. So these are all the shell codes. Now that is shell codes are low level code like assembly level code. That's why it's going to be specific to the operating system as well as specific to the processor. So here you see that the operating system of IBM, there is only one shell code that is available. But since we are working on x86 processor and Linux, so we are going to work on Linux and not ARM processor, but x86 processor. And x86 also not the 64-bit version of it, but we are going to look at the 32-bit version of it. So you see that there is a big list of shell codes, and each shell code they give the number of bytes also. So based on the buffer size, you can choose the right uh, shell code, right? So you see that this particular shell code can add a new root user to the password directory and also execute a shell, which is very complex operation, and that's why it's like almost 378 bytes. There are, so what we are looking for is maybe like /bin/ls. So we can actually look for /bin/sh. So you see there are so many source codes. Open one out of them actually. Mm, let's take the exact this is the exact one which I was talking about. So this is what is the shell code. So this is the instructions in x86, and this is the shell code. These are those bytes. Now you can test this shell codes very easily. So what you can do is just copy this shell. Okay, so I'm just copying this shell code, and I am copy pasting it into, maybe let me just take one of. Okay, so let me out of it. And so here I already have a shell code. Let me just show you that shell code. So this is the same shell code. Just runs a C program and causes a shell. So let us compile this first. So let us build it. The shell code is built, and you have that shell code. So let's execute that, and you see that I get a shell. This is a simple shell which I got as a part of the program execution. And what is this program? This set of instructions that were executed. That's it. So if you see, this is a function pointer which points to the variable shell code, which is this one, and it goes and execute this set of. What are these set of instructions? These are those set of instructions. I was able to get a shell. So easy as such to get a shell, right? But this is what we want to pass it as an input to our program. So let us go and open our program first. So let's go and open. So I call it as vuln.c. So this is the vulnerable program. In this, you see that in this 64 bytes of buffer, somehow we should inject this shell code, what we have got. So how do we do that? So we take the same technique which we have been following as of now. So we want to find out at what offset that data is. So this is the vulnerable binary. Let's do GDB Jeff and then pass it to the vulnerable program. It loads the program and first generate a pattern. So let's generate a pattern of 100 bytes again. Copy the pattern and run the program with this pattern, right? So once we run the program with this pattern, you'll see that it crashed at this location. You see the instruction pointer is also at that location. So let us tell that, can you search where this, so it is at an offset of 76 bytes. So the first thing we are going to do here is going to have our program with an offset of 72 bytes. So let me just put it here actually, so that we're going to have a set of A at 76 bytes offset. So that is 76 byte. And after that, we are going to have uh, the B with 4 bytes. So this is the return address actually. And that is a very simple program which can actually get a control for us. So let us give this. So that's a simple Python program, right? So let's go and execute that Python program first. You see that it is 76 A's followed by BBBB. So this BBBB is the return address. So let us test whether it is true or not. So let's run the binary with the Python code as an input. Once you execute it, you see that now the program stopped at 62, 62, 62, 62. What is 62 hexadecimal? So if you look at 62 hexadecimal over here, it is essentially nothing but BBBB. It means our guess that the return address is at this particular offset is correct. So now we got a hold of the return address. Now we have to put the shell code inside the program actually. So for that, let us understand a few concepts. So now we understand that we have the buffer, okay, and then the EBP old value, and then the return address, and then the parameters. So this is what is going to be for every. So what is the buffer size in our case? So you see that it's almost saying that to reach the return address, you should have at least 76 bytes of data. So it means from here to here, okay, this is nothing but 76 bytes of data. So this is 76 bytes of data. And then after 76 byte, whatever you put is nothing but going to be the return address. So what we want is, we want to put in this buffer our shell code. So it means I will just enlarge this buffer so that it's easy for us to understand. So this is that buffer actually, right? So this is the buffer, correct? So this buffer, well, I'm just putting it as a separate this thing. So this is the buffer. This buffer is going to be of size this plus this is going to be totally 76 byte. So here in this we want to put two things. One is our shell code. What is the shell code? So this set of instructions. So if you see our shell code here, right? So this shell of set of instructions, we want to put it into this address, and then make the return address point to the shell code here, right? So the return address should be here. So this is going to be our return address. So we want the return address to point here. So how do we get where it should point to? So it is going to be very difficult. So that's why we are going to fill this buffer with additional data, which is nothing but NOP instructions. So what is this NOP instruction? So if you see this NOP instruction, there is a special instruction with an opcode of 0x90 in x86, which the processor executes and does not do any operation. So it just simply executes, and it doesn't affect the processor state at all. What we're going to do is, we are going to create a set of NOP instruction followed by the shell code, and followed by the shell code is going to be our return address. So this is how it's going to look like. So we need a NOP code, then a shell code, followed by the return address. So these three things, how do we formulate? So there's a small Python code for doing that kind of functionality. Let me explain it to you. Here it is. Okay. So now we understand that our buffer is of size 76. And what is the code, shell code size? So if you remember, the shell code size is 23 bytes actually. So this whole number of bytes here over here is 23 bytes, right? And this is what we actually saw it here also. So if you see, it is 23 bytes. Can you see that? So now what we are going to do here is, we are saying that 23 bytes is the shell code. I'm putting some 33 bytes for the NOP instructions. So if you actually try to look at here, so what we are saying is 33 bytes for the NOP. So this is 33 bytes followed by 23 bytes of shell code, correct? And somehow we should jump ourselves to the instructions where the NOP is there actually. So we need to find what is the return address. Now I have given some return address here, and it's not going to be the same, but it may vary. And we'll find out how to debug that kind of problem actually. So what we are doing is, after that we are putting 20 times the return address. It means after 23 bytes, whatever is there, we are just going to fill it up with return addresses. Same return address. This return address is nothing but the place where it is going to jump to the NOP instruction. So let's go and execute this program, and that is how we are formulating the NOPs plus the shell code plus the return address after that actually, right? So let us see whether this works out or not. So let's quit the program. So run the Jeff with the, here we are going to run it with Python 2 and exploit.py and run it. Let's see what happens. So you see that it stopped, and it says that there is a segmentation fault, and it stopped at some address CF8A0, which doesn't look good actually, because we don't know what exactly it is. So that's why let's put a breakpoint. So we are putting a breakpoint at main, and another breakpoint we can put it is in our vulnerable function. Let's see where we can func. Okay, so where it's copying the buffer, it's at line number 9. So we put a breakpoint there, and then now run the program. So let's run the program. So it stopped at main function here. You see, let's continue, and you see that it's just about to copy the buffer here, right? I'm just reducing the size of the whole thing. So let's copy the buffer. So execute it. Now you see that onto my stack over here, the stack is all with 90. Now what is 90? As I told you, 90 is nothing but the NOP instructions actually, right? So it means it has copied all the whole stack with the buffer with the instructions 90. So let us take one out of this onto the stack because we want to jump to that location. So let's say C618, and let's put that onto our Python code. So here, let us put that address. So now what would happen is all our return addresses will be with, so it will return back to this NOP instructions and then continue the execution. So let us see whether it is, let's run the program again. Continue the execution. So you see that now we are at the place where it is going to have the NOP instruction. Let's go execute it. So you see now the instruction pointer is here. That is the place. Let's go to the next instruction. Next instruction. And you see that when it is going to return the vulnerable function, when it is returning back, now it is returning back to C618, and C618 is exactly the place where our NOP instructions are there, right? So let us go. So we see that, yeah. So you see that now the whole instructions are nothing but NOP instructions. So let's go and execute 5 instructions at a time. So ni5. So it is now 6 1 day. It is still NOP instructions. Let's go to next ni5 22, next 5, next 5, and next 5. You see that now it has come to the after the NOP instruction, it has come to XOR EX. Now what is the XOR EX? If you go and look at your shell code, what we looked at, you see that that is exactly the instruction which we were talking about. Same way you have after that a push instruction, right? 3 push instructions. So let us see whether there are there. You see there are 3 push instructions. There is a move instruction after that, right? So essentially it means now our shell code is getting executed. So when we are running this program, now if you say next, it is executing our shell code. And the shell code ends at int 80. So if you see here, the shell code ends at int 80. Hopefully, maybe we would be able to see something there. If not, I'll show you how to do that. You see that it executed it, went further, and it caused a segmentation kill, right? So it means at least our shell code got executed. We were able to inject our code inside the program and get a control to that. So what I will do now is I'll just execute the same thing, and we will run the program directly to it. Once we run the program, yeah, unfortunately it's still stuck there. So let me see one more time. So it actually, because I'm doing it in GDB, it's giving me a issue. But let me just demonstrate that to you in another set of program actually, which is this one. So essentially, this is the same program like Stack Overflow. So this is the same program which we discussed about, but slightly modified and more robust Python code I have written over here. So here what we are doing is we are creating a padding. So we have a return address also over here, and we have a set of NOPs and the payload, which is the shell code actually. So when I execute this code now, if you look at it, I'm passing that set of instructions as a part of it, and you see that we are able to get a shell. as a part of it. So it means I'm still executing this program, but I passed certain arguments to this or input to this program to execute my piece of code, which is nothing but a shell code. And now I'm able to go to maybe etc directory and see the content of the password files. So exactly like whatever a shell can do, I can all do that actually. So I can go and browse any directories which are available here and see the content of it. You see that? So that's how people hijack the program. And this is exactly what we are talking about in terms of the last one. So that last one, what we are talking about is nothing but we are able to inject a code which executes inside the program and get a control over the flow. So this is what is the danger thing about buffer overflows. So we started with a small thing and then started developing a very complex program where we can execute any arbitrary set of instructions on the processor. So that's what I wanted to show it to you and demonstrate it. So you might be thinking that how do I protect my binaries against these kind of attacks actually? So for that, we have typically these popular defense mechanisms. So why there were attacks on this whole set of programs out here, right? And it's mainly because that we did not use any of these mechanisms. Okay, so let's understand one by one each of these mechanisms. So as a developer, we did not do input validation. So if you see any of these programs which we wrote now, right? Any of these programs, whatever input is coming as a part of the argument, we are just blindly passing it to the functions and then copying that data blindly inside the buffer. So this is where the problem lies in. We are not validating whether the input should be ASCII character only, or it should be of the size of 10 bytes only, or 12 or 64 bytes in this case. Actually, we are just allowing blindly any number of bytes to be written, and that is what is a buffer overflow concept, right? So functions like strcpy, gets function, all these are dangerous functions. We should never use them because they override the data inside your local stack and can get a control over the system actually. Second is the OS itself gives some approaches, and which is like ASLR. One of them is address space layout and randomization. So I'll discuss about that. Then the compilers also give certain options, which is typically called as stack canaries. And apart from that, there are some defense mechanism, which is a combination of hardware, OS, as well as compilers all together. So we should actually employ these things to protect against these attacks. Actually. So as an input validation, I told you like you're not validating what input is coming in. So if we are able to validate that it is a set of instructions that are coming in, then it is good. It will never go into the data memory, and your program will never be compromised. Actually, that's why most of the attacks happen because of developers not writing code which validates the incoming input from external agents. Actually, when you talk about ASLR, so ASLR, as we remember, like every program is when it's loaded in the memory, it has these sections, right? So these sections are put into specific locations in the memory, right? Uh, so what OS does is every time you execute the program, it will put it at different location so that the attacker cannot guess these addresses. So if you remember, we actually were trying to find out these addresses. If this address is not correctly found, we cannot execute our shell code. So if this address is fixed, then attacker can easily find out. For every program, if this address is fixed, it is easy for him to know where the stack is located. But if the OS, when it loads the program in the memory, if it randomly loads at different locations, then it becomes difficult for the attacker to find out that okay, what is where it went, where it is loaded actually, right? So that is exactly what ASLR does actually, man. So if you look at ASLR, you see that every time you execute the program, so this is with respect to time, you see that all the segments are located at different locations in the RAM. It becomes very difficult for people to guess where exactly it happens. Now, how do you do that in Linux? So in Linux, there is a kernel variable called as randomized VA space, which is inside this directory path. If you make this as 0, then you are disabling the ASLR. If you make it as 2, then you are maximizing the effort of the OS to protect your binary and store it at different or load it at a different memory layout every time it is loaded in the memory. So let us actually write a small program. So this is the program which we're going to look at. It is nothing but executing assembly instruction where it is reading the value of ESP register. So ESP is stack pointer, right? It is reading the stack pointer hardware register, putting it into the integer variable I, and we're just printing the value of the I in hexadecimal value. So very simple program which just prints the stack pointer value, right? So let's see a demo of this. So at first, I will enable the ASLR. So if you see this enable script, it is nothing but we are putting the value 2 inside this randomized VA space. So it means we are telling that to the OS that every time I load a program, put it in different stack areas actually. And this is our stack pointer program. So the same program which I showed you, just taking the ESP value and printing out the ESP value. So we compile this program and then we execute the program. So first time I executed, you see the stack pointer is at a location A498. Next time I execute, you see now it is at 8E78. Next time I execute, it is at 7C18. It's totally random. So what happens is, as an attacker, I cannot now guess where exactly the stack is, because every time the processor is loading the stack at different location when it is executing the process. So this is one protection which is done by the OS. So let me just disable it now. So what disable is typically doing is putting a value 0 inside the variable. And now let's run the same executable, right? So we are executing it. First time we run, it is at C7A8. Second time also it is at C7A8. Third time also. It means that now there is no random place where the stack is put. Now precisely know that every time I execute the program, the stack is at this size. So as an attacker, I can get that advantage, and now I can use this for designing my payload and the shell code accordingly. So that is what is the ASLR concept. So this is the same demonstration which I showed you after disabling and enabling. Same way, there is some concept called as stack canary. So if you see, what happened is we had this buffer, and this buffer was overwriting the return value. So we are going to go and write, overflow the buffer, go and write the return address, and that's how we are getting control over the program. Now there is this concept called as function epilogue and prologue actually. So prologue is nothing but whenever you call a function, before calling the function, the compiler inserts a code which does some additional functionality. In this case, when you enable the canary, it does this function of canary wherein it inserts a random value in just between the buffer and the return address. Can you see? So it has inserted one random value over here. Now what happens is this random value is checked by the epilogue. Epilogue is when you return from the function. So what essentially you're doing is while entering the function, you're setting a value. While exiting a function, you are checking whether that value is set correctly, same or not. So if you override this buffer, it may happen that you have overwritten the canary value, and then it will fail during the epilogue actually. So to understand that, let's see this one. So this is your buffer. This is how it looks like. This is your return address. And since you have enabled canary, now you will see that between the buffer and the return address, the compiler has inserted a canary bit. Now, what would happen? when you write the shell code and you go on writing the addresses over here, it would have happened that you also overwritten the canary value. So before the function, it was dead here. Now the canary value is changed to FFFF because you, as an attacker, you are writing this data and overriding the return address. So the moment you return, the epilogue will check whether this canary value is same or not. Now it will find that it is different. So it will not return back to this address. So you see that the canary value will protect us to go and execute the shell code here. So that's how the canary value works in. So how does it work is nothing but you have to use this argument called as fstack protector. So when you use this argument with fstack protector, while compiling your C code, it adds that canary value. And you see that whenever the buffer is overloaded, it would actually show you a stack smashing error. So let's try it on our same program. If you remember, we had a buffer overflow program, right? So here you see that I have said purposefully that no stack protection, right? So instead of no stack protection, we will say that we want stack protection. So we will say that we want so now when we run the program and ask for the username, a normal thing works fine. But let's give a bigger buffer here, and you see that now it throws an error that there is a stack smashing detected, which was not true previously because we had disabled that protection. So every C program what you run, you should actually pass in this fstack protector to it, so that you can detect the stack smashing onto, right? So this is another program like mechanism to protect your program. And there is a third one, which is nothing but NX protection, which is nothing but no execution, or it's also called as DEP, data execution protection. So if you see every memory that is allocated, we can have these permissions: read, write, or execute, or a combination of these permissions. So essentially, we should make sure that our programs are given the right permissions, and the segments are given the right permission. So if you look at it, when we talked about the attack, so you remember that what happened is the user passed in the input to us and stored it into the data part of it, right? So if someone asks you what is the permissions you would like to give to the data out of these three permissions, so and what is the permissions you would like to give to the code? So if you see, the code segment should not be writable, but it should be executable and it should be readable. So Rx is the right permission for the code. And this is like precisely what we are talking here. But if you talk about the data segment, we should not be able to execute anything on the data. Right now, if you remember, all the data that came in resided in the stack, and we were able to execute also because it had execute permissions. So to protect it, we should actually make sure that the data segments are not marked with X, which is nothing but capable of executing the functionality. So it should be only read and write functionality. So how do you do that? So that is also controlled using a flag. This is like minus Z exec stack. So you should not give this while you are executing the program. Make sure that you should not use this flag. Otherwise, it allows you to execute the functionality on the stack actually. So if you do that, you see that you will get a segmentation fault like this, which would not allow you to execute the program actively. So this is another program. And if you look at what is seg fault 15, it is nothing but attempt to execute the code to a mapped memory location where the executable permissions are not there actually. So this is like what is about the defense mechanism. So we are just left with some 3-4 slides more. So let me just show it to you because there are some animations in that. So you might ask, like, how do I find these vulnerabilities uh, in the programs? Okay, so you can't do it manually. Here we knew that the buffer is of 32 bit size, so we passed more than 32 bytes and things like that. But in real complex program, it is very difficult for us to do that. So for that, people use this concept of fuzzing. So in fuzzing, what happens is you try to send a lot of test data to the programs and see that whether it is able to handle it properly or not. If it is able to handle it, it's good. But if it is not able to handle it, it will either crash the program, like we saw that we passed a buffer of bigger size and it caused a segmentation fault, or sometimes it will hang itself. So these two are like unique things. These are things which we should actually look for and use them for finding the vulnerabilities. So what essentially fuzzing does is it just randomly passes the values to the program of different sizes, different set of inputs, flipping the bits, flipping the bytes, all that kind of things of thing it will do actually. And then it will check whether any of these inputs were able to crash the program or not. So just to give you an example of it, you can typically take a set of inputs as a, if you know the inputs, you can give it as a input. Otherwise, it is capable of generating its own inputs, and it changes those input values at every iteration and passes to the program. And whenever there is a crash, then it will give you a report saying that when I pass this input, there is a crash. Then now you can go and research onto it and see that why it crashed using the debuggers and things like that. So that will give you a better insight of how the things work out actually. So just to give you a small understanding of how it works in, let me just show you. So this is how it works in actually. So this is coverage guided uh, what do you call it? So you see that when it passed the first set of inputs, it could only find the first green part of it, right? Then it could only see the next one, and as it goes, it is able to find a better path. So here you see input is green, then it found that if I pass input plus the, it will be correct. Then input the cow, then jumped, and then you see that I am able to even give additional input, and then after over it is able to crash. It means these fuzzers are smart enough that it also take considers the coverage as an input parameter. So as it cover because there could be multiple paths a program can take in a real scenario, they are capable of keeping a track of that and then accordingly give the set of inputs which would lead to a situation where it can be finding a deep crashes also actually then. So in the coverage, it actually takes input from the coverage also as an input and generates the new mutated inputs actually. So it's a feedback kind of mechanism. So that is what I had for the whole lecture. So I would just suggest some few books. These four books on reverse engineering are really very, very good books. I think you should read those books. Though there are some of them you find that it's like 2012, 2011. Don't worry because they are still today referred by many experts, and you should have them as a part of your library actually. Then, apart from that, there are these other five books also I recommend you to go through. Very interesting, and they are the core books that are published in this domain. Actually, they're kind of the Bible for this set of domain. I also acknowledge people because some of the slides I have taken it from Jeremy, and I've taken permission for him. If you want to really go and do a further little advanced course in this, you should go to RPSec. They have a free course which talks about the whole thing, and that's what I had actually. So, if there are there any questions which we can take up?
Yeah, participants, in case if you have any questions, you can quickly raise. Sir, they are typing on the chat box.
Okay. Yeah, so someone is asking how do you validate the user inputs? So typically there are a set of libraries that are available which allows you to validate. Like just to give an example, if it is an email ID, so the email ID is typically going to have certain special characters like at the rate followed by a domain name and things like that. So there are plenty of open source library which are there. We can actually use that. But in case you have some specialized inputs where these libraries are not useful, then you have to write your own validators. Like for example, if I am taking input as some specific format in the binary, and it has specific markers, like the header should start with some specific set of bytes, then I should write my own what do you call validators for that thing. But today most of the libraries are there which allows you to do you'll get most of it there actually, so you don't have to write everything from the scratch.
Next is how to read entire data on RAM.
Yeah, so there are utilities that are available. One good utility is DD. It is called as DD in Linux. If you that is, but for that you will have to have privileges. So it means you should be the root user on Linux or the administrator on Windows machine. But apart from that, for Windows, there are some other tools also that are available, some commercial tools, especially the forensics tools that are there. They have the capability to go and read the complete RAM and dump it. So, and that's also a very common method a lot of people follow, especially when they do malware analysis and forensics, because once they have a raw dump of it, then they actually carve the data to find out specific data which they are interested into. So in Linux, DD is like very commonly used. Thank you so much. It
Thank
was
you.
very
Thank you very
nice.
much.
Yeah, yeah. Thank you.
Thanks a lot, sir. Thank you, sir.
Thank you.